Welcome. This is one of a series of videos designed to introduce you to the various features and capabilities of SQL Data Warehouse. My name is Alan Jordan, and I'm the Product Owner and Development Manager for the SQL Data Warehouse software. In our agenda today, we will first look at the basic principles of data warehouse design and the concept of dimensional modeling. This will then lead us into discussions on star schemas, surrogate keys, and slowly changing dimensions. We will follow this up with a detailed demonstration of how SQL Data Warehouse implements these concepts. In the early days of data warehousing, it was common to design the data warehouse using the same principles that had long been established as best practices for online transaction processing design, or OLTP. We've now learned that this is not the best idea, and that we need to think differently about design for data warehouses. It all comes down to what we are trying to achieve. In an OLTP application, we need to design the database to support the processing of many different types of transactions, sales orders, purchase orders, and the like. We need to ensure that these transactions are processed in a consistent way and that they are all accounted for and correct. We also design the database to avoid data redundancy. For example, the description for a customer grouping code should only be in the customer group table. It should never be included in the customer table or a transaction table. This is known as third normal form design. It works very well when used by computer software, but it results in the data being spread across many tables, making it very difficult for humans to work with. Now let's consider what is important from a data warehouse perspective. The primary requirement of our data warehouse design is that it needs to be a place where people can easily access information. We absolutely do not need to process transactions. We don't need to price orders or to make general ledger postings. We need to support business intelligence and analytics applications. So how do we design for this? If you think about what your company does, you might say that we sell our products in various markets. And if you wanted to assess how well you are at doing that, you might say we measure our performance over time. There are three key words in these statements: products, markets, and time. These three fundamentals almost always apply to any business. The definition of these terms will vary across different organizations. A retailer might sell physical products in stores in different parts of the country. They know their target market, but they may not know the names of their customers. An energy utility or an insurance company sells services rather than physical products, and they always know who their customers are. The concept of dimensional modeling is based around these three fundamentals: product, market, and time. The concept was originally developed in the early 2000s by Ralph Kimball, who has written many books on the subject. The simplest way to visualize a dimensional model is to imagine it as a cube or a three-dimensional spreadsheet, where product, market, and time are the dimensions represented on the three axes. Market is usually synonymous with customer, and as such, I've used the term customer in these slides instead of market. When defining dimensions, we need to determine the lowest level of detail that we should use. For product, it is typically easy to do. Often product ID or SKU is the right choice. If we know who our customers are, we can use customer ID or account number for the customer dimension. But if we're selling hot dogs at a baseball stadium concession stand, we don't know our customer names. Instead, maybe we could use event ID for the customer or market dimension. For most businesses, the date of the transaction will be the lowest level of the time dimension, and we will use date in our examples. The intersection of the axes of the cube can represent the sale of a specific product to a customer at a point in time. At each point, we can record one or more facts, such as the quantity sold, the selling price, and the cost. Facts are always numeric, and as such, they can be aggregated. Each dimension has attributes. The attributes describe the various characteristics of the dimension. Products could have attributes such as product line, brand, and supplier. Customers may have attributes like customer type, demographic, and address. A date has the obvious attributes of month and year, but also others such as week number and quarter number. So far, we've only used the 3 basic dimensions, but in practice, you'll likely find that you need to include other dimensions too. Many pieces of data will easily be identified as an attribute of one of the 3 basic ones, but a few may actually be another dimension. Consider a business with many stores. Sales occur in different stores, so we obviously need to include store as part of our analysis. Store is not an attribute of product because the same product can be sold in different stores. Store is not an attribute of customer, since the customer can shop at different stores. Therefore, store must be its own dimension. It has attributes such as its address and maybe the name of its manager. It's also not always obvious whether a data item should be a fact or an attribute. If unsure, we should ask, can this value vary by transaction? If the answer is yes, as in the case of sales quantity, then it is obviously a fact. For something like item weight, it is likely an attribute of product. Many products will always have the same weight, but if you're selling apples by the pound, then of course weight would be a fact of the transaction. Cost may not be so obvious. Your unit cost for an item may change only rarely, in which case you might make it an attribute. However, your costs may change on a very regular basis, so it may be best tracked as a fact. So far, we have described the logical model. How do we implement this in the data warehouse design? We use a star schema structure. A star schema has one central fact table joined to any number of dimension tables. The fact table includes the relevant dimension values and all of the facts associated with the transaction. In this example, there are 4 dimensions: customer, product, store, and time. The facts are quantity, unit price, discount amount, net price, sales value, and margin. Each dimension table includes the attributes of that dimension. One important design criteria is that we always use single key joins. This simplifies the usage of the star schema. This design makes it very easy to create an SQL statement or query that joins these tables and possibly aggregates data using any combination of attribute values, such as brand, customer group, year, and month, as in this example. Think about the queries and SQL statements you currently need to use when reporting directly from your operational data. Is it ever this simple? Hopefully, we're now starting to see the power and benefit of a data warehouse designed using dimensional modeling. You'll probably implement a different star schema for each transaction type, and in most of them, the fact table will be the most detailed level available for that type of transaction from the source data. However, a fact table can also represent summary data. If you commonly analyze monthly product sales by store, consider building a fact table at that level, as in this example. Your queries and reports will perform even better and with even simpler SQL. Today's session is not intended to be a full discussion on all aspects of data modeling. As with any concept, there are special circumstances and edge cases which need to be handled, as well as things to avoid. When you start on this journey, I recommend that you read more about the subject. Ralph Kimball has several excellent resources on his website. Search for Kimball Dimensional Modeling and you'll find many resources. Moving on to surrogate keys. These are used in our dimension tables to replace the original keys or keys of the entity. They are always numeric values that are simply assigned using the next available number. If you are familiar with the concept of identity columns or row ID columns, these are essentially the same thing. The original key values that are replaced by the surrogate key are also included in the dimension table. And surrogate keys need to be assigned by the ETL process whenever a new row is written to the dimension table. So why do we use them? There are several reasons. Firstly, they can significantly simplify the joins between tables. Remember we said that a star schema should always use single key joins? Well, what if the operational data requires 4 key fields to make the join? A single surrogate key value replaces those 4 original keys. Another advantage is that they separate the logical joins in the database from the business values. So why is that useful? It allows for significant differences or changes to the key values in your operational database. For example, an upgrade to the source application may change the key structure of a table. A surrogate key separates that change to the logical design of the data warehouse. Alternatively, you may need to load and merge data from your core ERP system as well as a web application, where the key structure of related tables is very different. Another scenario is where you have multiple instances of the same source table, which maybe have duplicate keys. In that case, we need to handle and merge the data with duplicate values. Now, here's an example. We have separate instances of a customer database in the US and Canada. We want to merge them in the data warehouse, but they have duplicate key values. The surrogate key replaces the original keys and it easily allows us to do this. The original customer number value is retained in the data, and we also introduce the country code as a new attribute. Finally, we want to look at the concept of slowly changing dimensions. Slowly changing dimensions provides a solution to a common reporting issue caused by changes to the attributes of an entity over time. Typically, operational databases do not retain any history of attribute changes, and this often results in issues with time-based reporting. Let's take this simple example for a customer. We have 2 attributes, customer group and sales representative. These attributes are 2 important ways that we measure our sales performance. Over time, it's possible that these may change. In this case, our customer was originally classified as a small retailer. They grew their business and became a larger retail store. As such, we recategorized them as a major retailer. Later, a new sales rep was hired and assigned to the customer. The customer record in the operational database was simply updated with these changes when they occurred. The operational database has no knowledge of the prior values. If we run a sales report by customer group and sales representative with a year-on-year comparison, the report will be incorrect for prior years. A report run today looking at prior years will group all of 2022 sales for this customer in the major retailer bucket. It will also show that Rob McAdam made sales in 2023 before he was even hired. The concept of slowly changing dimensions was developed to solve this issue by tracking the attribute changes in the data warehouse. There are several different approaches as to how these changes are tracked. We won't go into the details of these approaches in our discussion today. Each one has its pros and cons, but most organizations find that the approach known as Type 2 slowly changing dimensions is the best solution. The ETL process that loads the dimension table is designed to identify changes to the tracked attributes of an entity. When a change is detected, a new row is written to the dimension table using a new surrogate key value. The existing row retains the previous values of all of the attributes of the entity. The dimension table also includes columns to specify the date range for which each version of the record is in effect. SQL Data Warehouse has full support for Type 2 slowly changing dimensions. Let's look at the table design from a SQL Data Warehouse perspective. Firstly, it must use a surrogate key. This allows us to store multiple records for the same customer. Each record must include an effective to-date value, identifying the last date on which this record was effective. The current record will be assigned some unknown future date. We typically use the highest possible date value, 9999-12-31. You can also include something like an effective from date column and a flag to indicate the current row value, but these are not really necessary. In the metadata definitions that describe the dimension table, we identify the attributes that we want to track as slowly changing dimensions. The ETL process will automatically detect the changes, create the new record, and update the existing record with today's date as its effective to date. In addition, the ETL process that loads transactions joins to the version of the entity that was current on the date of the transaction. This might seem rather complicated. In some respects it is, but SQL Data Warehouse makes it very, very easy to implement. So let's see how it's done. I'm going to do a demonstration here. I will build a customer dimension table that tracks slowly changing dimensions. Then I will create the extract or ETL process that loads the customer table from the source data and show how simple it is to automatically handle changes to customer attributes. Finally, we will have a look at how a transaction extract links transactions to the image of the customer that was in effect at the time of the transaction. Okay, so I'm switching here to my SQL Data Warehouse client. I'm working in an environment here for a fictitious custom company called Beachboard. This is our development environment. I'm going to start with creating a new dimension table. All of the tables in the SQL Data Warehouse are known as data sets, regardless of their purpose and usage. We use these different groupings to identify different types of tables. So I'm going to work in this dimension grouping. I already have two created, both a products table and a time dimension. So I'm going to create my customer table. I select the group, click the new button. I'm going to choose here that I'm going to manually define it. And the first thing I need to do is to give it a name. We support both the long SQL name, which can be up to 128 characters, and the mandatory short name that the DB2 database requires. I'm simply going to call it customer dimension. And that's obviously longer than 10 characters, so I need to give it a short name. Having difficulty spelling here, but we'll get it right. We'll just call it customers. We need to specify advanced properties for the data set. In this case, we want to say that it has a surrogate key and that we are going to track type 2 slowly changing dimensions. There are some other attributes, such as whether I want to try to store it on SSD rather than spinning disk and others. But the only one that I want to change here besides those is to specify that this is a star schema dimension table. That's just a descriptive attribute in my metadata. And clicking next, I can now add the data elements or the columns to the data set. I'm going to click the Add button. I have a list of data elements that have already been defined, and I'm just simply going to select from this list. My surrogate key is customer ID. This is an integer column, so I'll select that one first. My original customer number was a character 10 column called cust number. And I obviously want the customer name. And I'm going to include various attributes for the customer. So we'll start with customer category. That's the code value. And I'm also going to include the category description. If you remember back to the discussion on the difference between data warehouse and normal database design, one is that the third normal form concept results in many tables. You would never include this description table in an operational database. It would always be separated out into its own table. But in data warehouse, especially in dimensional modeling, that's absolutely sensible to include both grouping both codes and descriptions in the same table. So I'm just going to continue to do that. I've got a region description somewhere down here. Region code and description, and then a rep code and rep name. And we'll also include the address. So I'm going to use address line 1, address line 2, city, state, zip code, and we'll also include the telephone number. And lastly, I also need to include a date field to determine which is the date, the last date on which this record is in effect. So I'm going to find the effective to date data element. This is defined as a date. And that's all I need. So I click next. I need to specify the dimension of this data set, the primary key, which will be customer ID. This is our surrogate key. That's the only key that I need. I do need to specify the slowly changing dimension control elements. The first one, the mandatory one, is which date will be used for the effective to date. I only have one, which is fittingly called effective to date. So that's the one that must be selected. I also need to specify the current row effective to date value. Remember, this is the date on which it is effective until. We don't know what date it will change next, so we give it some unknown future date, and typically we use this date that is so far into the future that we will never reach it. It's possible to also include an effective from date and a current row flag. These are actually not necessary from the design, but some designers like to include them. I'm going to skip them. And now we need to specify which of the attributes of the customer record I want to track when they change. So customer number is the original customer number, so that's not something that really will change. Customer name, though, may change. Category may change. And if the category changes, the description would change also. So it's superfluous for us to change the description. They are tied together. So I'm just going to select the code values of grouping code, customer group, region, and rep code without their names and descriptions. I don't really care if the customer address changes. That's not an attribute that I ever report and group by. So I'm not going to worry about tracking changes to the address. But if they do move to a different city or state or zip code, I do want to track those. Telephone, again, is not something I use for reporting, so there's no need to track it. If I click next on this panel, it's going to give me a warning. An index has not been defined. When we are tracking slowly changing dimensions, we are required to create an index that is based on the original key of the data and effective to data. So I'm going to say by customer number give it a description, and add those two data elements. So customer number, that's the original key of the data, and effective to date. And then I uncheck the add another data element and click OK. So this index is required for the ETL to automatically track the slowly changing dimension changes. And the next panel, I can just specify who is the owner. We'll take the default owner and the default authorization list to secure it. I can type as much text as I like here to describe the purpose and usage of this table. It's a customer table. I don't really need to add anything more. So for now, I will just click finish. So I finished the design. It's now asking me which project I'm using. Whenever I'm designing something in SQL Data Warehouse, the development activity must be attached to a project. So that is my only available project. I will use that. And I'm going to specify that I don't want you to ask me again for this session. Just use this project until I sign off and sign on again. Yes, I want to build it. Now, maybe I'm lucky. Nope, I was too slow. So in that split second, we submitted a job that created the table, and he did some other work too. So very quickly, we spent more time talking about it than really doing it. We have now created our slowly changing dimension customer table. I could do a sample the data here. Of course, it's empty. We haven't loaded anything into it yet, but I can still query it. The last step that I need to do to make it available for use in an extract is to check it in. So the check-in process completes the development cycle and just tells the software that, hey, this is a production-ready entity. So now I'm going up to the extract program definitions folder. I have a group here, which again is called dimensions. So this is where I'm creating dimension extracts or dimension table extracts. Click new. I'm going to, oops, I didn't select it there. I must have missed it. There we go. So program name, I'm going to call it cust load. Give it a description. And the primary source of data is the custmast table. This exists in my source system. So this is the source system customer table. I do need to bring in those descriptions that we wanted to include. They all exist in these small lookup tables. So the customer category code table, the customer group code table, there is a sales rep code table, and a region table. So those four tables are required to bring in the descriptions that I want to load into the dimension table. And next, which table am I loading? It's the new customers table that I have just created. So we'll add that. Click next. Again, I can add some text here to describe the purpose and usage of this extract. I'm just going to hit finish. And now we have our overview of the extract process. I can see the tables that are being joined, and we have this little magnifying glass symbol at the bottom here. This is the piece that does the magic to track the slowly changing dimension changes. So let's visualize what's happening inside this box. First thing is that magic table here. So this is an automatic lookup table that compares the existing current row value in the data warehouse to the new values that are coming in from the source system. I need to join based on the original customer number, which is custno, and it's already made a join based on effective to date to a constant here that is defined as 999-1231. So this is our unknown effective to date. So this is the lookup mechanism that we've taken care of that. I now simply need to tell it how to join to these other lookup tables. I'm just moving them over so I don't have so far to drag. Customer group joins to customer group. Sales rep joins to the cusrep column. And this one's a little different. The region belongs to the rep, not to the customer. So I need to join that region key to the rep. So I have now defined my joins. And the last task is to do the source to target column mapping for the data elements. So I just expanded these. I'm going to sort based on the column sequence because that's just a little easier for me to complete the mappings. So customer, oops, I missed that. Customer number goes to customer number, customer name to name, category code to cuscat, description, group. As you see, it doesn't take long to complete the mappings. Okay, all done. So every column in our target table has a mapping from one of the source columns. So we'll save that and close it. Now we need to build it. So this extract job in SQL Data Warehouse is a compiled program, and that gives us stellar performance. So we'll just build it. And now it's ready to test. So I'm just going to hit the run button and various options that I can select here, but I don't need to select anything. I'm just going to hit run. And I'm probably not quick enough. Nope, there's only 100 rows of source data, so this takes less than a second to run. So it should have loaded my customers table. So I'm going to just take a look at the data. So I hit the sample button, and here it is. The first thing to see is our customer ID surrogate key has been assigned, starting at 1. All of the rows that were loaded today, I think there are 101 of them, they were all detected as being new rows. So it created new customer IDs. And because they are new rows, all of them are the current row for the customer. So all of them should have the future effective to date 9999/12/31. Okay, so that's my initial load. What then happens when a customer attribute changes? I have I'll close that. I have an Access Client Solutions SQL script session here, and I'm just going to run this first SQL that I've prepared. And this one finds all of the customers that where the city is Daytona Beach. So I've got 3 customers in Daytona Beach, and all of them have a sales representative, Elizabeth Green. Well, we've just hired a new sales rep. His name is Tom Huntington, and we're going to reassign these 3 customers to make Tom the sales rep. So I have an update somewhere here. Here it is, this one. So I've got an SQL statement to perform that update. So let me run it. And now if I run this next SQL, which looks at the source data, not the target data, we find that those 3 customers are now assigned to now have a sales rep of TH. So we've simulated an attribute change in the source system. Let's run the extract again. So it's going to process the same 101 source records and search for it. This time it will find that they are all existing customers, and it will do the slowly changing dimension attribute tracking. So let's sample the data again. So there are 3 changed customers in here. Those 3 changed customers should have a close date. So this has been here's one of them, and there should be two others. There's another one, and we should get to the very bottom. We should find that we now have 104 records in here. Remember, we had 101 previously. Let's go back to our SQL. Close that and run this prepared SQL, which is the first one that we ran, which is looking at all of the customers in the dimension table with an address with a city of Daytona Beach. And now we have 6 records. The original 3 records now have an effective to date, and this is actually yesterday's date. And there are 3 new records specifying that Tom is the sales rep, and they have the future unknown effective to date. So why is that yesterday's date and not today's date? Well, that's a choice that you need to make. By default, we assume that a change made today, anytime during the day today, is effective as at the start of the business day. So this is a decision you need to make. Should a change made at noon today be effective at the beginning of today, or is it a change that's effective at the beginning of tomorrow? And by default, we assume it's made at the beginning of the day. However, it's very easy to change it to say that it is that it should be tomorrow instead of today. And I can just show you how to do that. On this magic customer entity here, there is a column called closed row effective to date, and it has an automatically generated rule saying it's the job date minus 1 day. So if I want to make that change effective as at the end of today, I would simply edit that and remove the minus 1 day. And now it will treat changes made today effective as effective at the end of today. Your choice. Neither of those choices is correct or incorrect, just a decision you need to make when you're tracking those things. Okay, so we've now seen how easy it is to create both the dimension table and run then the ETL that loads it. Now, how do we attach transactions to the appropriate record in this dimension table? It would take a little bit of time to design the transaction ETL. It's a little bit more involved, but instead I'm going to switch to another environment, which is my completed development environment, where I already have a transaction extract that loads transactions. So this extract takes invoice information from the source system and loads it out into different data sets. The invoice line data set is at the lowest level. This is our fact table, transaction level. There's also a fact table here at a customer sales by year, and there's one that's comparing brand versus plan. So not really a fact table. It's a separate entity in the data warehouse. We are joining to the customers table as part of this extract. So this is our slowly changing dimension customer table. So let's have a look at how that join is done. If you remember, we have a secondary index based on any dimension table that is based on the original customer number and the effective to date. So this is the join right here. So we are joining from the customer number from the invoice, and we are also joining on effective to date. But notice that this join line is green, and this indicates that this, and if I can hit it correctly here, there we go. This is a position to join rather than an exact match join. And that position to, in conjunction with the type of join of get next matching row by partial key, will automatically find the next the record for this customer with a effective to date that is equal to or greater than the date of the transaction. So a transaction with today's date will join to will find the record that has the future unknown effective to date, whereas a transaction with yesterday's date for one of our 3 customers in Daytona Beach would find the old record, which was effective up until the end of day yesterday. So this is the simple mechanism that allows a transaction load to connect that transaction in the fact table to the entity that was in effect at the date of the transaction. So that concludes our demonstration and today's video. So I hope you enjoyed it. I hope it was informative. We are absolutely available to give you more information or a more in-depth demonstration.